All right, and our next speaker is Jeffrey Liccardello. Right, go ahead.
Great. Well, Karen, thanks very much. Thank you, everyone. We're happy to be here. My name's Gio Liccardello. I'm with the company Taraxis, and we are presenting you information on our high temperature vacuum pyrolysis reactor for processing lunar regolith. My contact information is here if you need to reach me after this presentation. I'm also joined by my colleagues Andreas Joachim and John Zelon. And we're low on time, so let's just dive into the next slide. So the main application for our reactor is ISRU processing of raw lunar regolith. The two key applications for this regolith processing are number one, oxygen extraction for obvious reasons for life support or scaled up for rocket engine propellant. But also with our high temperature approach here, we can also extract out many other elements from the mineral compounds of raw regolith, such as iron, aluminum, titanium, etc. And the vacuum pyrolysis approach is a high temperature approach that is not dependent on naturally occurring water deposits on the moon. Kevin had a wonderful presentation earlier today where he was going through all of the challenges with characterizing where water is and how much there is. The Viper mission, a lot of people are looking at natural water sources on the moon for good reason. But we're trying to sidestep that by processing regolith in its raw form and getting out the useful elements that we need. Um, let's go ahead to, okay, actually, before we move on, so this chart here, just to explain, this is at 100 pascals pressure. At what temperature different elements begin to dissociate from their parent compounds. And you can see there's a key inflection point at around 2000 degrees Celsius, and our prototype to date has exceeded that temperature. So we're starting to work within the really fun region where we can begin to extract all the good things that we want out of the raw regolith. Next slide, please. So on this slide, this is a system overview of where our system fits within a lunar infrastructure. And, you know, Jerry had a great presentation earlier today talking about all the different elements of ISRU, the different approaches people are taking. But where our focus is right now is what is within these sort of white rectangles on the screen here. So we are in sort of the reactor and refinement business. But we will need, as part of this lunar infrastructure, a system for collecting regolith and delivering it to the reactor. We're going to need power from a power station, whether that is PV arrays or maybe it's a solar concentrator running a Stirling engine, you know, whatever form it ends up being, power data, comms, etc. But we're going to take these mineral compounds in the regolith on the left-hand side, goes into our reactor, it gets superheated above critical temperatures, and then we can condense out different materials at different temperature gradients, ending with oxygen freezing out at cryogenic temperatures. That then gets separated, processed, stored, and then sent on to the end user, whoever that ends up being. I thought it was really interesting how Otis was talking about how to mechanically move regolith around in hoppers and things like that. Holly's talking about fabricating these simulants, and now here we are, the next stage of the process with the reactor processing them. So we think we're very well aligned with the goals of this workshop and all the great people here. Let's go to the next slide. So this slide is showing the functional description of our ground prototype as it exists in our lab today. Now in the top right corner, we've set a goal for ourselves of being able to produce, you know, pilot plant levels of O2, so 1 metric ton per year, using 20 kilowatts of power at a 50% duty cycle. So we're not processing when the sun is down. Our reactor to date is well aligned with those goals, we think, but there's still a lot of parts to nail down. But fundamentally here in the center of our diagram, we have our crucible, and that is going to be the vessel that holds the raw regolith. That crucible sits within a reaction chamber, which is held at a reduced pressure. That chamber has a thermal reflector shield around the surface area of the chamber to keep all of our heat energy, or as much heat energy as we can, within the reaction and eliminate waste heat. We have a liquid cooling loop on the left-hand side that's going to run around and keep all of our external surfaces cool. And then we have a power source. So on the ground, we're getting our energy from the grid, but it could be coming from a solar farm on the moon. We then condition that power through a series of drive control electronics, which drive a series of electromagnetic coils. Those coils wirelessly transmit power into the crucible, superheating up the contents to above the desired temperature. And then as they vaporize, we have a condenser that will begin condensing out the different products at different temperatures. Next slide, please. So this slide should actually have video, if there's any way. Oh, great, great. It's probably a little choppy with the telecon, but you can see this is our prototype that we have in the lab today. The crucible is sitting in the center of that chamber, and it's glowing very, very brightly because it's at around 2,000 degrees centigrade. And it's actually brighter than what you see because you're only seeing the light that's getting through our thermal reflector. And it's actually quite blinding to look at without that. Now, the way we measure temperature on this is we actually have an optical temperature probe that's looking into the center of the chamber. It's going to measure the spectrum that's being emitted by the crucible and then calculates out the resultant temperature based on fancy math. But yeah, so I think we are doing pretty good on time right now. Is that right, Karen? Okay, 2 minutes. All right, so before I move on, just last thing of note, you can see our liquid cooling running on the outside of this thing. And our test stand is kind of built up on a modular structure with a lot of 80/20, so we can swap in and out a lot of different hardware pretty easily. So it's designed for lots of rapid iteration, and it's gone through many evolutions over the last few years. Let's move on to the final slide. So lastly, we just want to talk to you guys about our preliminary roadmap for taking this technology forward to a pilot plant on the moon. So on the top of this chart, we have our kind of overall series of tasks and timelines, along with a series of discrete milestones where we're going to have to address each of the different engineering areas to turn this into a functional system. And we've been working on this reactor in its earliest form since 2017, though we've only actually formed as a company at the end of 2020. And we recently filed a patent for our current reactor. On the bottom left-hand side of the screen, we've got a list of all of our specific milestones that we're aiming to accomplish and when they occur. And then next to that, on the lower right-hand side of the screen, we've begun reaching out to different partners, whether it's academia or commercial or government, to help bring together the different pieces that we need to make this a functional system. Since really we're working on the reactor right now, but there's a lot of pieces to be put in place. So I think we're just about out of time, so I won't take up any more there, but we look forward to speaking with everyone in the breakout sessions, and thank you very much for your time.
All right, thanks so much.